Bismillahirrahmanirrahim. Assalamu alaikum, dear student. Welcome you all in my lecture 11. In this lecture, basically this is the end of cutoff bars and cutoff bending of bars theoretical. Theoretically, inshallah, we will complete this session, and after that, inshallah, we will start numerical on cutoff bars and uh, bending up bars. Okay. So this is the present topic is special requirements near the point of zero moment. This means that uh, whenever there are you know point of inflection, zero moment means where moments become zero, because we see in the continuous beam which is somewhat like this. So this is called point of inflection. This is called point of inflection. Similarly, if you see the bending moment diagram of simply supported beam, so they looks like this. Okay, so there are moment becomes zero, and this point it supports, the moment comes out to be zero. Clear? So at moment zero moment place, which is known as point of inflection, uh, ACI imposes some sort of restriction. Okay, at this location. Okay, whenever you are cutting bars at these points, you have to, you have to check that ACI criteria, and that ACI criteria is basically mm, this one. You have to check this ACI design criteria at the at point of inflection. Okay, so now we are basically dealing with that criteria, that you can say LD must be less than or equals to Mn, that is the nominal moment capacity, divided by the ultimate shear plus LA. LA is the length of the cutoff bars beyond the point of inflection. Okay, so this may be toward this side in the positive, and it should be remembered that this criteria should be checked for a positive moment only. It don't need to be checked in negative moment. Okay, because in positive region the the uh, the 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 bending moment curve is a concave convex upward. Okay, or you can say concave downward. But in the negative bending moment diagram, you see that its concavity is, downward. Okay, so it is in this shape. Clear? It is in this shape, but their concavity is down. Okay, this concavity is down, which means the convex surface is upward. Okay, the convexity, you can say, of the negative moment diagram is toward the beam side, but there is the convexity is in opposite direction of the beam length. Clear? So what I mean that basically if you draw a tangent, a tangent with this kind of curve, okay, at point of inflection, so you will get this kind of line. If you draw a tangent with this, so you will get this kind of line. And in negative moment, you don't need to, because if you are drawing tangent to this curve, it is coming inside, so that is not true. It must come out, it must comes out to be outside. Okay, so the tangent that if I extend that tangent in downward direction, so it will be like this. So you can see that the bending curve is far behind this tangent. Clear? So therefore you will see, inshallah we will discuss this matter. So this formula should be checked only for positive movement. Clear? Now uh, this is a kind of explanation of this topic. You see that this is a continuous beam, a portion is taken, and this is negative movement and this is positive movement. Clear? At point 3 you see that there is maximum movement. Clear? And you know, point 3, point 1 is a point of inflection, point 2 is a basically theoretical cutoff point. Okay, this is the maximum movement. Clear? This is the maximum movement. Okay, that is the ultimate maximum movement. Clear? Now from 3, you know, you have to provide LD. You know, if you are providing your steel bars to to support this maximum movement, you have to extend the bars or embed the bars into the concrete, both sides equal to a distance of LD. Clear? Now it says that if LD is reaches to point of inflection. Clear? In limiting case, you know, it says that some kind of limiting cases, its development in reaches to point of inflection. So what it means that the two, which is, you can say this is a theoretical cutoff point, which is, you can say this is the 1/3 of this moment. So if you know, if this is the 1/3 point, so as LD reaches to point of inflection, so you know, the moment which is right there, the bar will be extended to this side. For this point of movement will be, the development length of this bar will be 1/3 of the development length. Okay, for this point. So basically here just this problem right here. While the basic requirement for flexure tensile reinforcement is that a full development length LD be provided beyond the point where the bar is assumed fully stressed to a point. The requirement may not be sufficient to ensure safety against boundary stress. I explain you this point, that at this point, okay, this is the maximum movement point, and I assume there that bar should be stressed to a point. So it says that you need to provide to extend the bar both in this direction and both in this direction, both right to left of this point, which must be equal to the embedment length to ensure any kind of bond distress, bond failure. Clear? Now, figure 6.2 shows the moment and shear diagram representative of a uniformly loaded continuous beam. I already told you that this diagram is drawn for a uniformly distributed load and a continuous beam. So this is, and this is the shear diagram. Clear? For the same beam. Now, what I did, basically where the shear is 0, the moment is maximum. And this is the theoretical cutoff point, which is come here, and point of inflection is shown here. So the shear at the point of inflection is known to be VU. Clear? Now it says positive bars provided to resist the maximum movement at 3 are required to have a full development length beyond the point 3 measured in the direction of decreasing movement. I already mention you this point that the whole positive area should be provided at this point 3, and that bars must be extended to both direction this and this, to fulfill the development length requirement. Clear? Now, thus LD in the limiting case could be exactly equal to the distance from 3 point to the point of inflection. In most of limiting cases, it says that the development length starts from this point and reaches to the point of inflection. If this occurs, then what will happen? Okay, thus LD in the limiting case could be exactly equal to the distance from this point to inflection. However, if that requirement were exactly met, then at point 2, halfway from 3 to the point of inflection, those bars would have only one half. You can say one half their development length remaining. You know, this is the point which I am telling you. Okay, that if we consider that the moment is right here is you can say one half of that maximum moment, this maximum moment. So if I draw a vertical line at this point, so if the development length for point 3 is reaches to the point of inflection, then the development length which is available for this point, this theoretical point, which is half, where half movement is present, so the development length for this point will be L by 2. Okay, means as this point 2 is at the halfway from point of inflection. Clear? This is okay. This is the point of maximum movement, and it says that this length is basically LD. The development length for bars at 3 point is LD. Now the movement starts right there. This is the point of inflection. So this is the half movement. Now this is the total movement, and this point 2 is basically where it is halfway of the distance from 3 to distance of 3 to this point of inflection. So the development length for 2 will be LD divided by 2. Clear? Now one half their development length remaining, whereas the moment would be 3/4 of that at point 3. Okay, and 3/4 of the bar force must yet be developed. 1/3. This situation arises whenever the moments over the development length. Now, where this kind of situation occurred, it says this situation arises when the moments over the development length are greater than those corresponding to a linear reduction to 0. Therefore, the problem is a concern in the positive movement region of continuous uniformly loaded spans, but not in the negative movement region. Now, this is basically mean that this kind of situation is basically occurred where the movement is maximum along the development length. Okay, along the development length. This is basically I can explain you from this kind of diagram. If this is my movement diagram, clear? If this is my movement diagram and I want to construct the movement strength diagram. Okay, so as movement strength diagram, the line is not assumed to be parabolic. In that case, we basically construct a linear diagram. So So as this length is basically LD, and this distance is basically LD, if I assume that this is point A and this is point B, now if I draw a tangent with this line, okay, so for example, as we know that the bar which is right here having movement capacity equals to 0 because there is no development length. Once the bar covered the development length, it gave you a strength at B point. Clear? So if I draw a line like this, so this region basically which you will see here is, needs some attention. Clear? Because you can see as this line is comes out like this. Okay. So this triangular area is your moment strength area. But now you can see that the actual moment area, or you can say the curve, is a maximum S from the strength. So your beam moment carrying capacity is not enough to support this moment, this extra moment. You see this area, clear? This area, this is outside from the moment strength area. So basically to support this, you need to draw your tangent or your moment strength diagram should be tangential to this one. Okay. This means that to envelop this actual moment diagram. Clear? Now, this kind of situation, this kind of problem arises, the topic which we are discussing, okay, in this kind of situation. Clear? So, basically, as discussed in section 6.1, which is the chapter number 6, the bond force U. We will discuss this chapter basically at just in lecture 1. You must know that your bond strength along the length of the bar, this is your bond strength. Clear? This is your bond strength. If this is tension. Clear? So your bond strength along the length of the bar is proportional to the tension of this bar. Means change in bond strength will equals to change in tension along the length of the bar. Clear? You must know this point. And you also know that tension is basically where dt, it is the change in tension at point 1 and point 2. We will just this discussion fs1 minus fs2 at just of the beginning when we are discussing about bond. Clear? The change in the bar tension in the length dx, since dt dm by jd, I explained this in lecture 10 and 9, that tension is your tension is proportional to change in moment divided by jd, that is the lever arm. Clear? So basically from this relationship you can get that bond strength is proportional to bending moment along the length. If we keep these two constant, you can directly say that bond strength is proportional to moment. That is, the bond force per unit length of bar generated by bending is proportional to the slope of the moment diagram. Clear? This is very interesting. Okay. As you see that your U, that is the bond strength, comes out to be dm by dx. Okay, dx. Clear? Okay, 1 divided by jd. Now this is the movement diagram slope. This is basically slope. Okay, change in movement with respect to distance. So change in moment means with respect to distance is basically slope of the moment diagram. Clear? Now you see that this is u. So basically, you know that if this is the moment diagram, you know, so if I draw a tangent with this line, clear? Okay, if I draw tangents with these lines, so their tangents at this point, your tangent becomes horizontal. So this slope, and if I draw horizontal with this slope, clear? This is basically dm by dx. So your u is related with this change. If this change is more, your u will be more. Means that if there is greater change along the length in movement along the length of the bar, the force of the bond will be maximum. And you see that at the ends of the bar, means at the ends of the bending moment diagram, the change is maximum. The slope change is maximum. You see here, okay. But as you are going upward, your change with the change of slope, it become decreases. This slope is more than this slope, clear? And at the top, you can see that the moment the slope becomes zero. So at the midpoint, the bonds, you can say bond becomes zero because change in moment becomes zero. But at the inflection point, you see that your bond force will be maximum. Clear? So this is a very interesting knowledge. The maximum bond force U in the positive moment region would therefore be at the point of inflection. This is the point which I mentioned. Okay. That maximum bond force will occur where at the point of inflection, not at maximum point flash. Clear? This is a very interesting information which we get. Okay. Uh, I think you people would expect that there is the maximum movement, so maximum bond force will there. Not practically from this relationship, you can say that maximum bond force will be there because the change in movement is greater at this point because the change in movement at this point becomes zero. Okay, so what this sentence say, the maximum bound force U in the positive moment region, okay, would therefore be at the point of inflection, and U would gradually diminish, along the beam toward point 3. And that's what I say, that there is maximum, and as you are going upward, your force of bond will diminishing. Diminishing means decreasing. They will vanish. They will become zero. Okay, they get reduced, and at the point of 3 you will see that it becomes 0. Okay, so clearly a conservative approach in evaluating adequacy in bond for those bars that are continued as far as the point of inflection, not necessarily the full as provided for mu at point 3, would be to require that the bond resistance, which is assumed to increase linearly along the bar from its end, be governed by the maximum rate of movement increase, that is the maximum slope dm by dx to the moment diagram, which for positive bending is seen to occur at the inflection point. Clear? So it said that the maximum bar which is provided right there, so it has a maximum bond force will be seen at this point. Clear? So those bars which is extended to this point of inflection, its maximum bond force will be there and also will there. Okay. Now, because the slope of the moment diagram at any point is equal to the value of the shear force at the point. It is also basically from the mechanics. Okay, you must know that This is a very important relationship, that slope is basically equals to change in moment diagram. Clear? And you must know that load is basically equals to change in shear diagram. Okay? In a shear diagram, for example, this is the shear diagram. So at this point, the change in slope of the shear diagram with respect to x, it is basically equals to the load in the loading diagram. Clear? At this point, it will give you the rate of loading. And similarly, the change in movement at any point give you the change in shear. Okay, that is numerically equals to shear. A very important relationship. You people can search it in shear in engineering mechanics, or MOS1, MOS2, MOS1. Sorry. Uh, Now the slope of the movement diagram at the point of inflection is VU. Clearly, because at point of inflection, the slope, the change in movement with respect to x equals to V. With reference to figure 6.22, a dashed line may therefore be drawn tangent to the movement curve at the point of inflection, having the slope equal to the value of the shear. Then if Mn is the nominal flexural strength provided by those bars that extend to the point of inflection, and F movement diagram were conservatively assumed to vary linearly along the dashed line tangent, then we can say that, you know, what does it mean? This dashed line, you know, you see this dashed line. That dashed line is basically representing the moment strength diagram. We draw in example number 1. Okay, we basically consume a lot of time on that diagram. Clear? So, and that diagram, whenever we are constructing, you must recall that theory, that we draw a diagram like this. Okay, we draw a diagram like this. You must recall. So this line is basically assumed to be linear. So here what they did, they draw a tangent with this actual movement diagram, which is, like this case which I address here. Okay, the slope of this line must be greater than, it must envelop the actual movement diagram. It must envelop. Envelop means that it must lie outside of this actual movement curve. Okay, so you see that this line, clear, and this line is basically assumed to be extend for a distance of a. This distance is basically equals to a. Clear? This distance is basically equal to a. Clear? Now the moment capacity at the peak point of this line is assumed to be mn. That is the nominal moment capacity, not in terms of mu, because this is the moment strength diagram, and moment strength diagram is basically constructed on the principles of, you can say, on the equation of phi mn. So ignoring phi for the time being, just put mn. Okay, now as the line ends, so what will be this slope? Okay, what will be this slope? The slope is basically equals to change in the moment with respect to a. Clear? With respect to this length is basically equals to the slope at this point. Okay, this slope. Now as at this point, if you comes down and you see that at this point the shear is equals to Vu. So therefore we already say that the change in movement with respect to change in movement is basically equals to shear. So dmn divided by a comes out to be clear, and from there we can say that a, basically this distance a will be equals to what change in, or you can say that mn dividing by VU. Okay. VU. Mn dividing by VU. Okay. So this one, you get this equation. This distance A equals to Mn divided by VU. Okay. Now, if the bars, now you must know that Mn is basically the movement capacity of those bars which is extended right to the point of inflection. Okay. It is not necessary that all the bars which is provided here may be extended to this point, because in limiting stages it says at the beginning that development length reaches to the point of inflection, but most of time it may also happen that if this is the point of inflection start here and this one, and you provide the maximum bar for this maximum movement there, it may possible that the development then will be somewhat like there. Okay, it may lies somewhat like there. It may not possible that it will reaches to the point of inflection. So the bar which is provided, for example, if there are 4 bars, okay, so there are 2 bars. There are maybe possible 2 bars. There is possibility that there will be 4 bars. Okay, so these 4 bars having a moment capacity Mn. Okay, if these are 2, then it has a moment capacity of Mn. So in limiting cases, these bar development length reaches to the point of inflection. Not in all cases, clear? So if bars in question were fully stressed at a distance A, clear? At a distance A, to the right of the point of inflection. If the bars in question were fully stressed at a distance A to the right of the point of inflection, and if the moments diminished linearly to the point of inflection as suggested by the dashed line, then bond failure would not occur if the development length LD did not exceed the distance A. The actual moments are less than indicated by the dashed line, so the requirement is on the safe side. Clear? This is basically mean that this distance A which you are seeing here, this one, this is a such length that it assuming that this A, if it is such that the bar will fully stressed, full Fy strength is developed, you know so, and this length is equals to LD, or it equals to LD, or it is may greater than LD, so you can say that there will be no bond failure. Okay, because you see that the movement at this point of inflection comes to be 0. Okay, and as well as you also see that the line which is tangential to the actual movement diagram, you know it envelops the actual movement diagram. Its slope is maximum as compared to the movement diagram, actual movement diagram. So therefore you can say we are on a safe side. But if this A is greater than LD or equals to LD, okay, and this LD is basically somewhat far away from the point of inflection. So as the moment at this point becomes 0, so you don't need this distance, clear, behind that point of bar, clear. But if you are extending the bar behind the point of inflection, you are making yourself to be more safe, clear. This distance LA you see here, this distance LA, this is a kind of extension behind the point of inflection. Okay, so this extension make you more safe. Okay, you this LA basically making you more safe. Okay, so if you not extend and your A must be equals to LD, okay, are greater than LD, then you are on safe side. Your bond failure would not occur. Clear? So this sentence as basic meaning is that clear. If the bar extends past the point of inflection toward the support, for example, if your LD, or you can say your air distance is more than your LD, okay, like that, okay. There you can say your air distance increases from or equals to LD at a distance of LA, okay. So what will happen then if the bar extends past the point of inflection? Past the point of inflection, it extends to a distance toward the support as is always required. It is required, practically be provided. Then the extension can be counted as contributing towards satisfying the requirement for embedment length. Arbitrarily, according to a CI code, this is restriction. A length past the point of inflection not greater than the larger of the beam D or 12 times, okay, the bar diameter may be counted towards satisfying the requirement. Thus, the requirement for, you know, this means basically what it basically means, you know, you see this kind of relationship, clear, that you know this A is basically, it is a distance at which in which you can say your whole bond, your bar stress is produced, okay. So this is a kind of embedment length, a kind of embedment length. Now if you are making more safe yourself, you must need ACI code says that you have to extend your bar from this point of inflection toward the support in a positive moment region toward the support at a distance of LA. It basically, inshallah, you will see in numericals. You will more clear on this topic in numerical. Okay, don't worry. LA must be equals to, I already mentioned you that this distance must be equal to D or 12 times of diameter of bar. This is effective lift, this is diameter of bar. So, and in the almost in all cases we take LA is equal to 6 inches. Clear? So, from this, okay, you can say that your LD must be equals to our, now we can get that relationship that your this distance LD means your LA, the extension beyond the point of inflection, and the distance to the nominal moment capacity, which is A from the point of inflection, is both A and LA. When you add up these 2 points, your LA plus your A, you know this distance must be greater than, must be equal to your development length. Okay, this distance must be. This means that, at the beginning I will mention you that at point 2, the bar, if the bar is extended from point 3 to this point of inflection of a distance of LD. Now the moment which is right over the point 2, okay, it has only remain a development length which is equals to the half of the total development length. Now we justify that distance, clear, that distance A. Basically we are justifying that distance here, that whether that distance is sufficient to develop the full stress or not. Okay, so they justified that distance, that your A distance, plus some extra extension, that distance must be greater than or equal to LD. And as you know that LD should be less than or equal to, A is basically equals to, we derived it from Mn divided by Mn divided by Vu plus La. Clear? So inshallah, whenever we are solving our problems, we must solving our problems relating to beams in which point of inflection occurs. So we will check this. Okay, we will check this. Okay, and similarly, this case arises in a simply supported beam. Clear? When we are dealing with simply supported beams, clear? Whenever we are dealing with simply supported beams, so in a simply supported beam at the support this point, this kind of problem is also occur. And at that point, inshallah, we will see that we will adjust, we will check for this moment. Clear? We will also check because at simply supported, you know, there are supports, and the movement starts from, you know, the movement starts here like this. So the support movement is zero. Okay, movement is zero. So basically, we will also use this derived formula here because and remember that there we will take uh, our LD must be less than or equal to 1.3. A factor is multiplied with the Mn. Clear? Divided by Vu plus La. Clear? 1.3 factor is basically multiplied. It is a kind of increases the amount of nominal moment because at the support in simply supported beam there is a kind of compressive forces developed due to the bearing stresses. There is support because you must know that when you provide a support to a beam like that, so this is the bearing area. Clear? This is the bearing area, and in this bearing area there are bearing stresses. Due to bearing stresses, sometimes this support there is a tendency of cracks develops. Okay, uh, a kind of compressive forces would occur there, and that compressive forces develops for some extra compression in the steel. Clear? So due to that compression, the the bond forces will get reduced. So this effect will move for larger size of bars, and smaller will be for lesser size of bars. Smaller size of bars, this effect will less, and for larger size of bars, this effect will more. Okay, so we will check this this formula at the supports of simply supported beams. And this point and this problem is also, if you are interested to see this problem basically. So mgregor basically adjust or you can say explain this problem clear. And basically you see here, okay, this is the simply supported beam, this is the bearing plate, and a kind of potential cracks occurred. This is the bearing area. So if you want to, due to this cracks, bearing stresses is produced, which creating a compressive forces in the steel. Okay, so to control this problem, we provide some extra reinforcement. Okay, you see this reinforcement, clear? So this is a kind of bars welded with the actual bars. Okay, to control that crack, and this chamfer is provided. So this kind of arrangement basically made in precast concrete members. Clear? So this kind of check will be used for, this is for inflection point, and this will be for simply supported beam. Clear? Because there are some kind of flexion. I also uh, discuss this problem because if you are drawing your tangent line from A to B, and this shaded area, because this is the actual movement diagram, so your actual movement diagram is now outside from your strength movement diagram. So in this region, you know, the actual moment will be more than your moment capacity. Okay, so you are not on a safe side. You need that your tangent OA must be envelop the actual moment, which is the required moment diagram. Okay, so here you will say, now you will determine this slope. That slope will be the moment mn at point A change with the distance dx. Okay, so basically they relate, this is your vu pi mn divided by ld. Okay, and ld will be equals to now, and remember that this length from point A to point O, horizontal length, is must be equals to ld. In the Nielsen book, they assume that this distance equals to a. Clear? They assume this distance equals to a, but mcgregor basically assumed that distance must be equal to ld. I already mentioned you that your horizontal distance a must be greater than or must be equals to ld. That if you want the movement, movement strength, which is mn at this point a, if you want that point, your this horizontal distance must be equals to development length or must be greater than equal to development length. So that is the air distance, and we then provide some extension, some kind of extension LA, which we through which we are satisfying ourselves more satisfaction. We will making more safe ourselves. Clear? So basically, LD phi I mean this one, and some imposing some kind of other satisfaction or safety. Basically that distance you don't know that that distance will be equals to ld. Clear? So making your more ensuring yourself, or means you are making more safe yourself, you add some extra link with the develop with that distance a. Okay, you add some distance a. Okay, because this distance here they assume that this is equals to ld. Now they assume it. Basically it may equals to ld, or it may greater than ld, or it may possible that this distance will be less than ld. So so to remove that ambiguity, we add some extra link with this ld, that is la. So in that Nielsen book, we basically assume that this is distance a, and making safe ourselves, we add distance la, some extra length la, which is equals to dr 12 dB with this a. Okay, so making ourselves more safe. So in this case, ld must be less than sorry or equals to a plus la, means your this distance must be greater than or equal to ld. Clear? So this equation is derived 1.3 mn. Basically it is for simple supports. Clear? Because there is bearing stresses. Okay, and for general point of inflection like you see in continuous beams, okay, you just only use mn divided by vu. So inshallah, we there is an example. We did this example on this topic. Clear? Time is so. Inshallah, we will do this example in our next lecture. Clear? And basically, we also cover some part of the other example. Inshallah. So for the time being, I think this is enough. You must need to recall this theory, because this theory should be, should very very important. We use this trick in our next coming example. So if you have any question, any doubts, I welcome.